Hello and welcome to Apologetics 101. I'm your host, Brian, your resident Christian apologist. And we're here today with Dr. Andrew Snelling to discuss radiometric dating. This is a video that I've been waiting for a very long time. And before we jump into that, I just want to point out the fact that I'm not going in the strict order that I originally planned. It's just too long to wait for videos on particular topics I really like, but I can't do because I'm waiting for me to get to a particular chapter with the Genesis series. So what I decided to do instead is topologically, although some of the topics will still try to stick to the chapter by chapter commentary of Genesis 1 through 11, it will on occasion, I might sit there and bring up topics or uh, uh, topics that may be not quite as relevant to one chapter as it is another. But even then, I will only do it with the topological stuff. So all the commentary stuff on Genesis 1 to 11 be in order. I'm not going to be doing chapter 8 before I do chapter 5, for example. So that will still be in order. The topological stuff, for the most part, will probably be close to being in order. It's just that I will probably go out of order on some of the issues, just because there's a lot of talk on my channel, a lot of comments and stuff concerning radiometric dating. A lot of people like the subject matter, either people who want to believe in radiometric dating versus the ones who obviously have problems with it and have responses and reputation to claims concerning radiometric dating. And we are and I wanted to sit there and just kind of address that. And I always wanted to do for a while now a big video specifically targeting radiometric dating. And me and Dr. Andrew Snelling does that. I always wanted to do it with Dr. Snelling, actually. He's my favorite geologist, and I always wanted him to do this discussion with me. So it was a pleasure, honor to do this with him. And I asked him all the right questions concerning that. Now, we had a lot of technical issues initially. The devil really did not want this video to happen. In a bad way. I had technical issues on my side. My Wi-Fi messed up. I had this little dongle thing connected to my thing, and it got bent, and it wouldn't work. So I couldn't go do the internet on here. So I went to the my other computer to do it. But there's a reason why I don't do YouTube videos on that computer anymore. It's an all-in-one. Its memory is shot pretty much, and it causes my videos to freeze, and it starts to freeze up a lot. A lot of bugs start happening, buggy kind of stuff starts happening with it. I could not get anything to load properly. Couldn't get anything to. Some things just froze up my computer, and it was all kinds of problems. Trying to even get into Zoom was an issue, and so finally, I like, okay, I've got this little router box. Can't show it to you right now. It's off screen. It's connected to my internet, but it's like this white box. It connects the signal to the other router downstairs. So it's one of those things, and I knew that if I connect it with an Ethernet cord to my computer, it'll be like connecting it directly to a wireless like a router, directly to a router, which essentially that's what it is. It's a router, but it will connect to the one downstairs because that's the one that connects to my actual internet. And so I'm like, okay, but I don't have an Ethernet cord. A friend of mine was asleep early this morning when I was trying to get all this thing settled. Um, and then finally, went down there. I was able to get a hold of him, and he let me borrow his Ethernet cord. He told me just borrow it for whatever time I need it. He said he's not really using it right now, so I said, okay, thank you. So I'm borrowing his Ethernet cord right now so that I can have internet on this particular computer because I can't really do YouTube videos on that computer anymore. It just has way too many problems doing it. I can use it generally as a computer, but I can't sit there and use it to to do the kind of stuff that I do on my YouTube channel and interviews and things like that. So I had all kinds of technical problems. I finally got that resolved, and as soon as I did, and me and Dr. Snelling was able to get to our meeting. Dr. Snelling had some technical problems. He could speak in the microphone where I can hear him, but he could not hear me, and it was on his end. He even said he couldn't play videos or nothing. And so we were working with that for the longest time. Finally, I said, my wife is the tech whiz of the family, so I went down and got my wife, and she came up and helped Dr. Snelling get his computer right so that he could be able to hear me. And so so the devil did not want this to happen, but it did, and it was a blast. And me and Dr. Snelling had fun. It was pretty cool discussion, and we were able to respond to a lot of criticisms that were made by the critics and the other sides, including the most popular arguments that they place on the internet and on popular websites and popular responses to the rate team's research and things like that. So we were able to deal with a lot of different things, and so it was pretty cool. I loved it, and I hope you guys love it too. And without further ado, let's dive in. Hello, and welcome to Apologetics 101. I'm here today with Dr. Andrew Snelling, and today we're going to be discussing radiometric dating. Um, Actually, we have had a lot of technical difficulties trying to get to this meeting. Go ahead and introduce yourself, Dr. Snelling.
I'm Dr. Andrew Snelling, a native Australian. Grew up in Sydney and trained in geology with a PhD in geology from the University of Sydney. I then did some work in the mining industry in field and project and field research and project research, including with government agencies. I have been involved in creation ministry now for over 40 years. I was part of the radioisotopes and age of the Earth group at the Institute for Creation Research, where I worked for 9 years. I'm still with Answers in Genesis. I've been their director of research. I've started two technical journals, creationist technical journals, and so I've been in a lot of research over the years, and that's my call to fame.
Are you still the editor of Answers Research Journal?
I'm handing that over at the moment to Dr. Georgia Purdy because I lived in the USA for 13 years in northern Kentucky, but we've just moved back to Australia so we can be close to our families again. But I'm still working remotely, and now with the technology, it's possible to be anywhere in the world and be involved. So yes, I'm still involved in editing the journal and writing papers. Currently writing some papers at the moment, so it keeps me busy.
Awesome. All right. So we've had a lot of technical difficulties. Like I said, I've had technical difficulties on my end. You had technical difficulties on your end. So the devil's really been fighting us on this one.
For
So,
sure.
so I'm so happy we managed to get to it. All right. I guess we can go ahead and jump in. You got my questions right that I had sent you.
Yes.
All right. All right. Well, I guess we start with the first question. I usually like to start with something basic so that everybody kind of knows what's what. And in this case, I want to start with what exactly is radiometric dating, how the whole process of radioactive active elements decay, If you want to speak to things like beta decay and things like that, I know I got those as separate questions, but you can go ahead and speak to beta decay and alpha decay and different kinds of
Yeah,
decay.
what happens is that each element has a number of isotopes, which is based on the size of the nucleus, how many neutrons are in the nucleus. The number of protons determines the element number. So, for example, regular carbon has 6 protons and 6 neutrons in its nucleus, so that's carbon 12. But you also get carbon 14. It has 14 particles in its nucleus, so it has 8 neutrons. But that means the nucleus becomes unstable and it wants to downsize, so to speak, to become stable. And so it spits out particles. And so the bigger the atom, the more particles it can spit out. So you got uranium-238, which is 238 particles in its nucleus, element 92, so it's 92 protons. So it's got so many neutrons that it decides to spit some of those out to become more stable. And so the particles that get ejected from the nucleus are what's detected with radiation detectors. That's what is radioactive decay. And so radioactive dating of rocks is based on this decay process where an atom like uranium-238, which is radioactive, we call that the parent, spits out particles, alpha particles, which is two neutrons and 2 protons, and so it's quite heavy, and that's why you detect it very easily. Damages tissues, it damages rocks, etc., and leaves damage trails. But we can figure out the daughter product, that is the resulting atom that after the decay occurs, you get a daughter atom. So you got a parent-daughter pair. So you got potassium decays to argon, rubidium to strontium, uranium to lead. And so what we do, if you measure in a rock or mineral the amount of lead product that is there today, and therefore you know how many parent uranium atoms had to decay to produce that amount of daughter atoms. If you know the rate at which it decays, then you know how long ago the decay process started. You assume that's when the rock formed, and so that becomes the date or age that you produce. So it's quite a simple process in one sense, but there's a lot of assumptions involved, which I'm sure we'll come to in a moment. And so a parent decays to a daughter, and if you know how many daughters atoms you have today, you know how quickly the parent decays, then you can calculate how long ago there were no daughters, and therefore that's when the process started, and that must be the age of your rock, how long ago the rock formed. So that's the nuts and bolts, the simple explanation for radioactive decay, and that's how it works.
What exactly is like beta decay and alpha decay and electron capture and neutron capture?
Okay, alpha decay is where you have an alpha particle spat out, which is 2 protons and 2 neutrons. And what happens, of course, is that alpha particle will pick up stray electrons and add it, and it becomes helium, because 2 protons and 2 neutrons is the nucleus of a helium atom. All it has to do is find some electrons and it produces helium. So actually, helium is a byproduct of uranium decaying to lead, and we'll come back to helium eventually. Beta decay is where an electron is spat out. A neutron is made up of a proton and electron. That's why it's negative charge, And if it spits out electron, it leaves a proton behind. And so that changes the element. So the element, so for example, carbon-14 decays to nitrogen, to nitrogen, and nitrogen is element 7. So it's got one more proton. So it adds a proton to make a different element. So that's beta decay. Neutron capture is where the atom captures a neutron and adds it to its nucleus, so it increases its nuclear size. Electron capture is where the element captures an electron. The nucleus captures electron, usually taken from one of the inner shells, and so the electron being captured by the nucleus combines with a proton to produce another neutron. And so, the nuclear physicists are well versed with these sorts of processes. They understand them, and they're well studied.
Right. And if I'm understanding this correctly, whenever an unstable element will continue to decay until it gets to a stable element, is that right? Or will it?
Yes, that's right. Some do it directly. Some do it via a series of steps. So uranium goes through a whole decay chain. It produces thorium, and that decays and that produces radium, radon, polonium, lead, until it gets to the stable end members. So you got the uranium decay chain or uranium decay series. There's also, that's 238. There's also 235 uranium. It has a slightly different decay series with a different end member. Lead 207, uranium 238 ends with lead 206. And so, but potassium, it decays to argon, but it does by what we call branch decay. Some of the potassium decays to calcium 40. And so you've got to know the branching ratio to figure out how to do the calculations. But generally, all that's worked out. Rubidium decays to strontium. That's a direct step. There's no decay series there. And it depends. It varies from element to element as to exactly, and to isotope exactly what the decay steps are.
This might come more into play as we're moving forward, but what exactly is relative ages and absolute ages? That might be something that might come as essential as we're discussing this, especially
Yeah,
with
well,
assumptions.
a relative age is you look older than your son, so you're relatively older than your son. Um, you get look at the Grand Canyon. You look over the rim, and you see all these layers stacked up on top of one another. We know that water carries materials and deposits it, and so the layers at the bottom of any sequence are older relative to the layers higher in a sequence, because it's like cooking pancakes on a griddle, and you take them off the griddle and stack them on the plate. The pancake at the bottom of the pile on the plate was cooked first on the griddle, and so it's relatively older than the pancake at the top of the stack. How old the difference, we don't know, unless you've got a clock there which records what time it was that you cooked the first pancake and what time it was that you cooked the last pancake. And so absolute time is where you've got a clock that can actually measure what the time was when the process started. And so radioactive dating is supposed to produce absolute ages. It's supposed to be a clock that times when a rock originally formed based on measurements today. You look at a clock today and you see where the hour hand is and where the minute hand is. You actually read the clock so you can tell the time. Well, that's what the geologist does they measure the parent and the daughter, and by using that as a clock, they can work out an absolute time. That's radiometric dating. Whereas relative dating is the layers relative to one another. So a granite, for example, a granite will come as a hot molten blob and intrude into pre-existing layers. So those layers are older than the granite. The granite is younger because it's been pushed into it. So a volcano erupts and the lava spill on top of the layers on the ground that cover the ground. So the layers on the ground are older than the lavas. The lavas are more recent. So that's relative time. Whereas if you want to know how old the lavas are, you take samples and do radiometric dating to get an absolute age.
Okay, is radiometric dating really absolute age, or is that just what they think it is?
Well, it's based on assumptions.
Yeah,
And
let's go
assumptions,
ahead and hit the assumptions, because that's my next question anyhow. What assumptions
yeah.
are radiometric?
The assumptions with radiometric dating is that first of all, you have to know the initial conditions. Okay. Were there any daughters already in the rock when it formed? Or were there no daughter atoms in the rock when it formed? You've got to know the initial conditions. You've got to know that during the time the clock has been ticking, the system has been closed. In other words, there's been no leakage out of the system, because daughter atoms might leak out of the system, or parent atoms might leak out, or they might leak in and contaminate the system. So you've got to know the initial conditions. You've got to assume the initial conditions. You've got to assume that it's been a closed system, no contamination, and you've got to know the decay rate. If the rate hasn't been constant, then your clock isn't valid. What if decay rates were different in the past to what they are today? Then you've got no way of knowing how fast the clock was ticking during the time since the rock formed. And that's the problem, because the geologists weren't there when the rock formed to measure the initial conditions or the rate of decay when the rock formed. And then they weren't there over the time since the rock formed, between when the rock formed and today, to check that the system has been closed, that there's been no contamination. What if when the rock formed and inherited daughter atoms, that when we measure those today, we think that those daughter atoms were a result of decay of the parent, when in fact they were in the rock to begin with. Then the rock is going to date older than what it truly is. What if some of the daughter atoms leaked out? Then again, the rock is going to appear younger, because there's going to be fewer daughter atoms. And so there are all these sorts of issues that we have to overcome in being sure whether our clock is reading the right absolute age for the rock.
Right. And on these assumptions,
So
go ahead.
yeah, I was going to add that the important thing is, Brian, is that none of these assumptions are provable, because we weren't there in the past to test things. We've only got the present to test. So none of them are provable. And in fact, they're unreasonable. Why is it? And we know from experience that rocks do inherit daughter isotopes when they form. And we can go into this in more detail, but we know from recent lava flows on ocean islands that they inherit daughter isotopes, lead, argon, all these daughter atoms are inherited from the source. And so we know from experience today that that's the case. Well, why wasn't that the case back when the rock formed in the past? Maybe it was the same in the ancient past. We can't be sure because we weren't there. Contamination is a problem, because we know that, say, uranium, for example, is highly can dissolve easily, and it can dissolve in groundwaters. I earned my living working in the uranium exploration industry, and I could sample groundwaters to test them for uranium. And I knew where I was near a uranium deposit because the levels of uranium in the groundwaters went up. And, so the systems are not closed. They can leak out, they can leak in. We know that in the present world. So how can we assume that it's been perfectly reasonable through the so-called millions of years? And then the rate. We've only measured the rate in the laboratories today. And, one of my research projects, I looked at each of these parent atoms that are used in radioactive dating to check on the measurements that have been made in the last 100 years. And believe it or not, I couldn't find records. I went back decades with the different measurements and the different techniques, and I discovered that there were difficulties in getting the same results, decade after decade after decade. There was some variability, and so they're still trying to figure out what are the decay rates. They think they have it figured out for uranium, but even there are a few issues that they're totally unresolved. And the irony is I found out that in order to make the decay, if they dated a rock with two different methods, to get the methods to agree, they had to adjust the decay rate of the other method against the uranium decay rate to get the agreement. And so there was this all sorts of juggling to get the methods to work. And so these are the problems with these methods and the assumptions.
Right. If they had a eyewitness source, though, they could then be able to justify how old something is, because then you have someone that was actually present in those events.
Oh yes,
But
yes. In fact, we know that from historical records as to when certain volcanoes erupted. And so, for example, and all of this is in the literature, by the way, the conventional literature. It's not me making it up. G. Brent Dalrymple, who was the deputy director of the US Geological Survey and went on to work at the laboratory, the geochronology laboratory at UC Berkeley, the Berkeley Geochronology Laboratory. He potassium argon dated historic lava flows and published his results in the 1960s to show that historical lava flows gave potassium argon ages that were too old, sometimes by millions of years. And that was because there was argon in the volcanic gases that was trapped in the lavas when they crystallized. And so argon was added that when you then analyzed, if you assumed it had all come from potassium decay, it gave you an erroneous old age. And so
right.
we know that for historic lava flows. The question is, would that be the same for ancient lava flows? And the answer is probably. We weren't there, but it makes sense. If we're looking at the present as the key to the past, which is the mantra of conventional geology, then the problems we experience in the present should be the same problems we experience in the past. And so if known age rocks give you wrong results, then what about the unknown rocks from the ancient past? Could it be that they're not giving you the right ages as well? The answer is yes.
Right. I have a question on that. Since you brought the experiments up on known rock ages and volcanic rocks, there are some critics that there's a lot of critics that online that are bringing this up. They're claiming that if a rock is too young, that it cannot be dated. I don't understand they never really give any scientific argument for it. They just
No,
say,
they don't. And that's the problem. And that's why it's interesting. I'll give you an example. Okay. I've already told you about G. Brent Dalrymple, who did that exactly. He did it. He took historic young lavas and dated them with potassium argon and got erroneous old ages. Now, he was an expert in potassium argon dating, working at the Geochronology Laboratory at the University of California, Berkeley. Okay. Now, when Steve Austin a creationist, collected samples at Mount St. Helens from the post-1980 eruptions, lava flows in the new lava dome, and he sent the potassium argon dating. He was criticised for doing exactly what Brent Dalrymple had done, and Brent Dalrymple was one of the critics. Now, come on, let's get real. If the experts are doing it, they can't, and it's documented in literature, you can't turn around and then criticise creationists for doing exactly the same thing. And that's what I find a problem with all these critical critics and bloggers. They accuse creationists of doing things, the very things that conventional scientists have done. And you know, it's the pot calling the kettle black.
Right. Like I said, this is a kind of a popular criticism, but nobody's actually given any kind of scientific rationale for it at all. They just claim
No,
it, and then they'll give some kind of arbitrary number, like, "Oh, well, it has to be 100,000 years old." It's like, okay, why would you think it has to be 100,000 years old?
well, why did I know it will come up later, but why did they try to argon date the Vesuvius eruption?
Yeah,
That's a recent historic lava flow, right? So they were doing it. And
yeah,
and and so, for example, you can fly into the big island of Hawaii. You fly into Kona, and right by the airport there are lava flows. The golf course is built on them from 1801 and 1802. They give potassium argon ages by G. Brent Dalrymple himself. The paper is published in Earth and Planetary Science Letters, a reputable scientific journal, and it gave ages of millions of years. And the explanation was because it had inherited argon. There was excess argon in the rock. That is a well-known problem. So don't tell me that creation scientists are not real scientists if they're doing exactly the same thing as conventional scientists. The
yes,
critics, I'm sorry, but I call the critics out because they're not being consistent.
right. It seems more like a rescue device because they only started saying that after they realized, oh, wait a minute, known rocks are not, giving age consistent with what the radiometric dating methods are given. And like you said,
And
Mount Vesuvius had excess argon in that sample too. Is that right?
well, they successfully dated it with argon. I'm not sure there was. I can't recall the details as to whether there was excess argon in it or not.
Yeah.
But they
Well,
did get a.
I read it in the
You're probably right. If it's
literature.
documented in the literature, that's right. But here's the deal. When they can't criticize the science, they criticize the scientists.
Right. Um, I did tell that to another critic because how can you sit there say 100,000 years that it would take, and then you try to use the Mount Vesuvius incident when that's less than 2,000 years old.
Exactly. It's arbitrary.
Right. Right. Absolutely. All right. Um, could you discuss isochron dating method? And some critics bring up isochron as if that's supposed to somehow validate radiometric dating. Could you
Yeah.
speak to
Well, the isochron method is tries to get around the problem of the initial conditions and contamination. And basically, you're using multiple samples. So if you take a single sample, you use what is called the model age equation. You plug in the analyses, and you get a model age from a single sample. The isochron method works on multiple samples. Okay, you collect multiple samples from the same rock unit, from the same rock layer, from the same granite, whatever it is, lava flow. And we know that some samples will have more potassium, others will have less. More potassium means more argon, less potassium means less argon. And so you can plot, for example, potassium versus argon with all these different samples. And you put a straight line through them. So if you start at 0, and you've got potassium here, and you've got argon in your vertical axis, less potassium will produce less argon, more potassium will produce more argon. So the samples will line up on a line which is supposed to be the same age. It's called an isochron, same chron age. And so if that line goes through 0, then we know that the initial conditions were 0. If that line goes through some argon, we know there was some argon initially in the system. If some data points don't fit on the line, those must be contamination because they don't lie on the line. And so isochron dating is supposed to be a very powerful tool because effectively you don't have to necessarily measure the absolute amounts. You can measure the ratios. So, for example, lead-206 is the end member of uranium-238, but lead-204 is regular garden variety lead. It's common lead, it's not radioactive, etc. So in a mass spectrometer, the instrument you can measure, you actually can distinguish ratios of elements of isotopes to one another. So you can measure, say, uranium-238 against lead-204, and you can measure lead-206 against lead-204, and then you can plot the uranium-238 ratio over 204 over lead-206 over 204, and you can get an isochron. And so it's a very powerful method. The interesting thing is that you can go to the literature and you will find papers that will say not every isochron is a true isochron. They can be mixing lines. And I'll give you an example in a moment, or several examples. The same I recently saw, just a day or two ago, I saw a paper that's about to be published from the lab at Curtin University in Perth in Western Australia, where they've got isochron dates for zircon grains for some of the oldest rocks found on the planet. And it's a beautiful isochron, and they've discovered that it's not a true isochron. And they documented why it's not a true isochron. In other words, it's not giving the true age of the rock because it's had extra daughter lead added to the system, mixing in, it's created a mixing line. There's a classic study being done on the Isle of Skye off the northwest coast of Scotland, where they've looked at the lavas there, and they show that the isotopes in those lavas are a mixture of the lavas themselves and their source in the mantle, plus the rocks in which they came through, that they were contaminated, the basement rocks, the Louisian basement rocks. Another example, I did a study with a scientist from the government agency, the CSIRO, Commonwealth Scientific Industrial Research Organisation. It's well known internationally. It's an Australian government research agency. And we sampled over soil samples over a uranium deposit that I was involved in working on. And we collected samples further and further away from that uranium deposit. And when we plotted their lead isotope ratios, it produced a perfect isochron. The soil samples lined up with the samples from over the rock unit, the ore body itself. And so it was a mixing line of lead isotopes. It wasn't the age of the soil because the soil was recent. And so not all true isochrons are isochrons, and that's well known in the literature. They can be mixing lines, even if they're perfect isochrons without any hint of samples off the line. It's a perfect fit. And so It's now been recognised that even isochron dating has its problems.
Awesome. Um, you mentioned, okay, you talked about the assumptions of radiometric dating. One of those assumptions is that the the decay rate is consistent, that it's constant. Have we been able to, because some people think it's impossible to, even to the point where they think that we're violating physics, um, to that think that somehow that radiometric decay rates cannot be faster than what we can measure them in the present. But my understanding is that there are laboratory experiments that have been done to speed up radiometric decay. Is that correct?
Yes, radium is in the literature. There's a paper on radium where they and I can't recall the exact experimental conditions, but they speeded up the decay rate of radium. And theoretically, we know it's possible without breaking any laws of physics. All you have to do is change the binding forces in the nucleus by a small amount, and you get orders of change in the decay rate, speed it up. And so, without breaking any laws of physics, uh, you've got conservation of everything. Um, but theoretical physicists have looked into this, and you can go into the literature, and it's well documented. They've actually done experimental simulations and proven that small tweaking of the strong and weak nuclear forces holding the nucleus together can accelerate the decay rate orders of magnitude. We also know that it depends whether you refer to um, the particles as waves. I mean, they talk about tunneling. They talk about potential wells. They talk about Coulomb barriers. The theoretical physicists have delved into all these issues, and given the right experimental conditions, they see no reason why you cannot change the decay rates, speed them up or slow them down.
One
And
and
that's all in the theoretical literature.
Right. And one experiment, they actually increased radiometric decay by a factor of 1 billion. I know at
Correct.
least one, maybe more than one.
Correct. Yes. I'm aware of those as well. So it's not as if it hasn't been done, and it hasn't violated any laws of physics in doing it.
Right. In one experiment, I think they stripped the electrons and it just uh,
Correct.
it just depends on what conditions. Some people think that the condition that because of what they think on the strong and weak nuclear forces, that the outside the conditions it wouldn't matter what conditions it face. But we all know that that's false because they've actually have seen radiometric decay speed up even at room temperature. It's like,
Yes. That's right. Exactly. Exactly.
right,
And that makes a huge difference. And here's the thing, we can look at present conditions and we can draw conclusions from that. But what about, what goes on in a nuclear explosion, nuclear reactor? Um, you got to look at conditions that are beyond the normal conditions. What would happen in a catastrophe? I mean, geologists have learnt this. Something occurs in a catastrophe where geological rates are speeded up beyond their wildest expectations. Things that they would regard taking thousands of years to happen almost instantaneously. So, we've got to be very careful about projecting the present day processes and assuming that's the only way things can happen.
right. Um, let's see. Okay. Hey, are there any? Some people think that the radiometric dating proves that the world's 4.5 billion years old. Has any radiometric dating method been used on Earth rocks to date the Earth at 4.5 billion years. I understand. My understanding is that they actually get these dates from meteorites and moon rocks and things like that.
Correct, correct. It was done in the 1960s by Claire Patterson at Caltech, and he took a group of iron meteorites and analyzed their lead isotopes, and he produced a isochron 4.57 billion years, and the meteorites are assumed to be parts of the cores of a planet that disintegrated. You can go to, say, 4 Vesta, which is the 4th largest Vesta as an asteroid, and some of the meteorites match what we know of the composition there, and we know that they have a core, a mantle, and a crust, like some of the rocky planets do. And so the meteorites reflect a disintegrated, maybe extraplanet or leftover planetary materials that they assume came out of the solar nebula. And so if everything came out of the solar nebula at the same time, including the Earth, then the age you derive from the meteorites should be the same, give you the Earth's age. Now, of course, that's assuming that the Earth came out of the sun, that the sun was there first, which of course is an assumption. It's not a biblical assumption, because the Bible doesn't say that God made the sun before the Earth.
Right.
And so that's the problem. You've got secondary assumptions, but it's true. The so-called geochron, or age of the Earth, was determined on meteorites. He also took the lead isotope composition of a modern oceanic sediment, and that was supposed to be integration of lead isotopes over time, and that fitted onto that isochron determined from the meteorite. So he assumed that therefore was compatible with an age of the Earth of 4.5 billion years. We've found crystals that give you ages of over 4 billion years. And exactly it's some of those crystals that I was referring to a moment ago that gave a false isochron. A perfect isochron, but is now known not to be a true isochron. And that was on some of these crystals that are supposed to be from the oldest rock so far discovered, which happens to be in Western Australia, I'm proud to say.
Are you speaking of zircon crystals? Or are you saying, or talking about a different kind?
Yes. Zircon crystals, yes.
All right. Now, since we're already on that, and part of the rate team research is that they discovered that there was an abundance of helium inside zircon crystals, and I know that certain type of radiometric decays give off helium as a byproduct. Is that right?
Yes, uranium decay produces helium. Alpha particles are helium nuclei that I mentioned earlier, 2 protons, 2 neutrons. So once they're spat out of a uranium atom, they pick up stray electrons and become helium atoms. And so they're actually inside the crystals of say, zircon. You get lead and helium inside the zircon crystal that can be analyzed. And by the way, what we work was done back in the 1980s on a drill hole near Los Alamos in New Mexico, Fenton Hill. It was a drill hole that was put down to look for geothermal energy potential, and zircon crystals from the granodiorite that were being drilled into had different amounts of helium in them at different depths according to their temperatures. And so we know that helium leaks out the higher the temperature. You know, the more energetic the helium atoms become because they vibrate, and they slip out easier between in the crystal lattice of the the zirconium and silicon and oxygen atoms that make up the lattice of a zircon crystal. So they can easily leak out or slip out. And this is actually used as a dating method, by the way. But you have to know the leakage rate, and that's the problem. We measured the leakage rate at lower temperatures than what they did in the lab, and we found that the leakage rate at low temperatures was much faster than they'd realised. And even though the rocks were supposedly 1.5 billion years old, based on the lead composition in the zircon, the helium, based on the leakage rate, indicated the crystals and the rock were only about 6,000 years old, much younger. And so there was a disparity. And that indicated that a lot of decay must have occurred very rapidly to produce that amount of lead and helium in the rock.
And of course, if the zircon crystals were or billions of years old, or the granite that the zircon crystals are in were billions of years old, then there should be no helium in it, or virtually none.
Yeah, that's right. It should have leaked. It should have leaked out. That's right. But there's still lots of helium left in the crystals. And knowing the leakage rate, we know how much is leaked out. We can figure out how long ago the leakage started.
I got kind of distracted by my technical difficulties that we were having, but I got both of the books here for Rate Team's research, and also a non-technical one, Thousands Not Billions. Dr. Don DeYoung's was on the Rate Team as well. But my understanding from the Rate research on that is that after billions of years there should be no helium left in, and there's surrounding the biotite material there was also helium in there too, so that
Correct.
there's actually helium. And y'all know, and is it my understanding that y'all actually tested to make sure that the helium was intrinsic to the crystals, that it's not somehow, you
Oh
know,
yes,
yeah.
yes. The work was done in a recognised laboratory. We didn't do the work in our own laboratory because we get accused of fudging the results. So we sent the samples of the zircon crystals to a recognised laboratory that did the analyses for us by the standard equipment that they use to do their own analyses. And they had done, and they're published in the literature. And, this is used as a dating method. Um, they use uranium, thorium, helium dating, for example, to know, and they've used it, for example, in the Grand Canyon, to know how long the surface of the rock has been exposed, because the helium is going to leak out at the surface, and so they do calculate. So that's why they claim, the Grand Canyon was exhumed by the Colorado River supposedly 6 to 17 million years ago in different parts of the canyon. They can actually use the uranium, thorium, helium method. So, you know, critics will accuse creationists of using an invalid method and making claims about helium, but the conventional scientific community uses the same methods. And yet the problem with their methodology is they're using the wrong diffusion rates, because they've measured the leakage at higher temperatures, not at the low temperatures. We measured it at low temperatures, the low temperatures approaching what you get at the surface today, would be a more valid way of doing uranium, thorium, helium dating, using the leakage rate at the surface today.
Do scientists also pick and choose what radiometric dating that they would use? Like radiometric dating methods. Now, some people will try to argue that all radiometric dating methods give them the same results, but in reality, that's not true. Is that correct?
Well, it's like having a set of hourglass clocks with different size sand grains, different size atoms. If you start them all at time zero, the sand grains should all fall according to the size of their sand grains, and you should have the present time. Each clock should give you the same time since the rock formed, the same real time. Um, Now, because of that assumption that all the methods should give you the same result, the geologists choose which method is the most likely to be valid for the rock that they're dating. So, for example, a lava flow which is young, relatively young, they'll probably prefer potassium argon or argon argon. Maybe they'll do uranium lead on zircon crystals in the lava. I don't know. They could choose to do that. But they wouldn't choose rubidium strontium necessarily because it's a slower decayer. But if they've got an older lava flow, they might use rubidium strontium because there's been more time supposedly for more strontium to accumulate. And so they will pick and choose which methods they use based on the half-life, the decay rate of the parent isotope, sort of matching what they expect the age to be.
Well, that's the later
But
part.
it is true.
I was gonna
That's right. It is true though that if you take rocks, and we did this in the rate project, we took samples of rocks, say in the Grand Canyon. We took a number of rock units, lava flows in the eastern Grand Canyon, and the potassium argon isochron age was 516 million years. The rubidium strontium isochron age was nearly 1.1 billion or 1,100 million years. And the Sumerian neodymium age was 1,588 million years, 3 times the size of the potassium argon age. Different methods gave radically different results. We went to the central Grand Canyon where the lava, instead of coming to the surface and flowing out, was squeezed like toothpaste between the layers and hardened underground. We call it a sill. And the rock is a diabase, which is a coarsely crystalline basalt. And we dated it by 4 different methods, and we got 4 different results. The potassium argon age was again the youngest. The rubidium strontium was the second youngest. The samarium neodymium and uranium lead were the oldest. There was a difference between the beta decayers and the alpha decayers. The alpha decayers gave older ages, and the heavier the atom, the larger the age. So we did this with a number of rock units, and therefore there was a systematic process going on. And we figured it out. The only way to reconcile those different ages is that the decay rates were speeded up by different amounts at some catastrophic event in the past. So that, for example, in the lavas in the eastern Grand Canyon, while the potassium argon clock was ticking through 516 million years, the rubidium strontium clock was ticking through 1,100 million years, and the Sumerian neodymium clock was ticking through 1,588 million years. It was ticking 3 times faster than the potassium argon clock. That was the only way that you could reconcile those different ages. So that means decay rates were speeded up by different amounts according to the size or atomic weight of the parent radioactive atom. And so, and it's not that just we found that in the literature. I alluded to this before. We found it in our own studies, but it's also there in the literature where when they have tried different methods on the same rock, they don't always agree. And so, for example, there's a volcanic rock on the shores of Lake Superior, northeast of Duluth, Minnesota, that they sampled and they dated it with potassium argon, and they got a younger age than the uranium lead. To get agreement between those 2 ages, they said, maybe we don't know the decay rate of potassium properly, if we adjust the decay rate of potassium, we'll get the two methods to agree. Well, that's that's fudging it, so to speak.
How much do
And
you
so,
think, I was going to say, how much do you think that their presuppositions on how old they think something is plays into their choice of which radiometric dating method they use? Do you think they actually try to narrow
yeah,
it
well,
down to how old they think it is?
yeah, the target age is usually determines the method. It also determines which results are deemed acceptable or not too. And so, um,
Would this be
you know,
circular?
they'll reject ages if they're not what expected.
Would this be kind of circular where they're just kind of assuming their position, how old they think it is, and then pick and choose which one's best fit?
Correct. So you get situations where um, a 20 million year old um, granite in the Himalayas, dated by rubidium strontium or potassium argon, will have in it zircons that give you ages of hundreds of and thousands of millions of years. There's a granite in the Himalayas where the zircon crystals gave you a lead age of billions of years, whereas monazite, which is calcium phosphate with uranium in it, the monazite gave you a negative age, minus 97 million years from lead dating. I mean, come on, and then they assume, well, the zircon grains must have been inherited. Well, how do you know that? They crystallize from the granite when the granite forms. There's all sorts of issues like this that are well documented in the literature. In actual fact, you'll find them in that rate books you held up, the blue one, which is the first volume. I did a survey from the textbooks on radioactive dating, and they bring up all these issues, the textbooks, and document them from the conventional literature. So it's not me that's raising these issues. These issues have been raised in the conventional literature, and they're well documented.
Right. Um, and some people try to argue that some of the things that the creationists bring up, they indicate that the age is not billions of years old. They call them anomalies. Have you heard that where someone will say, "Well, y'all just keep bringing up these anomalies"? To me, an anomaly would be something that like a fluke of nature, something that's a once over. But if you're finding C14 in every diamond or every coal, it doesn't strike me as an anomaly. But
No, that's right, and that's here's the deal. Um, Russ Humphreys looked at all the different methods that have been used to try and date the Earth, and he discovered that over 90% of them give a young age. So, in other words, the less than 10% are the anomalies that give an old age. And so the anomalies are the old ages, not the young ages. It's the opposite.
right. And while we're on that subject matter, C14 in diamonds, this was a big one in the rate team's research, and it's still brought up today. The fact that they found C14, abundance of C14 in diamonds. They tested, what was it, 10 or 12 diamonds or something like that? Did y'all test it?
Yes.
And it was found
Yes.
C14 in it. And
And we've been testing more since.
good. And they try, and there are people that try to try to argue for some kind of contamination. Have you heard of
Well,
these arguments before?
I certainly have. And let's back up a minute.
Okay.
In 2004, we put a we published a poster at the fall meeting of the American Geophysical Union in San Francisco. That's the largest meeting of geoscientists in the world. Over 10,000 geoscientists gather every year. And this poster was reporting on the finding of radiocarbon in diamonds. One of those who saw that was the director of the radiocarbon lab at the University of California, Riverside. He went back to his own lab, got his own diamonds, and replicated our results. And his results found radiocarbon in the diamonds, and he published those results himself in the conventional literature. So don't tell me that it's just us replicating the results. No. Is it contamination? Well, first of all, diamonds are the hardest known substance. They're very pure. You can't contaminate them, or things can't get out. They're very hard. They're very resilient, and so it's not Some say, well, wait a minute. You get nitrogen, you get gas bubbles with nitrogen in them inside the diamond, and you might get some uranium. And if the uranium decays, the neutrons can hit the nitrogen atoms and produce carbon-14. The answer is yes, that can happen. But in the rate book, you will find the calculations based on the amount of uranium and nitrogen known to be in diamonds, how much carbon-14 that should be, and it's far less than what was detected. So,
Yeah.
the critics haven't even looked at the calculations that are there that we did to rule out that argument.
Also, if I understand correctly, y'all found that they would have to actually have thousands of times more than what they actually did, in
Correct.
order
Correct.
to account for it. Um,
Correct.
just the basically what they're doing is they're taking things with very fat or slow decay rates, and they're trying to replenish something with a very fast decay rate, and that's
Correct.
silly because you're not going to be able to get that. You might get some, like you said, you might get some C14 to develop from that, but you're not going to get as much as what we found. Um,
And
and
we found it's in the literature that what happened is that when radiocarbon dating was first uh, worked out, the methodology, the instruments used a beta decay, detected beta decays. But the problem is cosmic radiation can affect your instrument. So you had to shield everything in lead bricks to keep out the cosmic radiation. Well, in the 1980s, they developed a different technology called accelerator mass spectrometry, which can actually count individual carbon atoms. Very, very, one in a trillion atoms they can measure. And here's the thing: is they discovered that, okay, let's test our equipment to see what the background is. And they discovered they put in coal samples that were supposed to be hundreds of millions of years old, and they got radiocarbon in them. They got marble that was supposed to be millions of years old, and they got radiocarbon in it. And they thought, well, is this contamination? They didn't have anything in their equipment and got zero. And so that meant that it had to be intrinsic to whatever they were putting into their equipment. And here's the thing: if every atom of the Earth was radiocarbon, within a million years it should all be gone. So if the coal was truly hundreds of millions of years old, it shouldn't have any radiocarbon in it, just like dinosaur bones shouldn't have any radiocarbon in it. But dinosaur bones give radiocarbon ages of only thousands of years. And in the second rate book, we did an experiment. We report on the results where we got coal samples from the repository, the US Department of Energy repository, that were 40 million years, the same radiocarbon age, because they were all alive at the same day, the day before the flood. And so that wasn't surprising.
Baumgartner has a really interesting article. It's a very technical article. I think it's good enough to be peer reviewed, but it's actually on the Answers in Genesis website, challenging these claims. And he does a really good job of showing that. And basically, if I understand Baumgartner's arguments as well, is that the findings were well above the laboratory threshold for contamination.
Correct.
Like if you got
Absolutely.
like really really low and it's like higher than what is it was expected for that particular laboratory in terms of contamination.
Oh, absolutely.
Maybe put it somewhere and say, okay, we're just going to sit here on the shelf and
No, no. The coal samples were from.
and some people, one guy that I was debating has another particular position where he thinks that it was contaminated between when the diamonds went from unprocessed to processed. Um, do you know what he's talking about there?
Uh, no, I don't, because you can the diamonds. Some of the diamonds we did both deep earth, from hard rock, and you know um, they're not processed. Process would be
Okay, for some reason it cuts off here in the recording. I don't know why. I didn't edit it at this part. It literally, I saw it in the editing where it just kind of skips over this spot. I think something happened with the recording or something. It just kind of jumped over that particular point, and I don't know why. But essentially, it's a very short portion it skipped over. But Dr. Snelling was describing what was considered to be processed diamonds versus unprocessed diamonds, and he said was saying processed diamonds would be like if you cut the diamond and the diamond is being used for like a ring or something like that. That's what he was basically describing. I don't know why the recording skipped, but I figured I'd add that in so you understand what he actually said. I didn't edit that out. It's just something happened with the recording. I don't know what it was. Um, and uh,
and like I said, it was replicated in the UC Riverside Radiocarbon Laboratory.
right. Um, uh, on the terms of the assumptions, the assumption is, of course, that the radio oil sample hasn't been contaminated for long periods of time in terms of that. Some people, one guy tried to argue that we could tell if it's been contaminated because he. I sent you the question. Let me see if I can find it real quick. Okay. Some have said that we can graph radioactive elements to see if it's linear or not to determine if contamination has happened. Is this true or false? This is an exact quote from him. He says, it assumes that no contamination in the rock has occurred. He's stating our position there. He says, this is also patently false. We know that it can and does happen, and we could tell when it has. If it has occurred, the data on the isochron plot will not be linear. It will be determined with uranium-lead dating with coordinate discoordinate graphs. Is that what you were talking about earlier? Like that someone thinks
Correct.
it's
Correct. Correct.
later, but it's
Yeah, you can get isochrons that are not true isochrons. I mean, back in the 1980s, they were talking about mantle isochrons, um, that were a result of the chemistry of the mantle source of the lava flows. That wasn't anything to do with the age of the rock. I mean, not all isochrons are true isochrons. They can look perfect, and yet they can be due to contamination and mixing. Yes, it's true that if a sample doesn't plot on the isochron, it's possibly due to contamination. I say possibly because it may be that the sample that doesn't fit on the isochron is actually the true uncontaminated. The ones that fit on the line might be contamination, which they've actually shown. It could be a mixing lines, and I gave you examples of those from the Isle of Skye, from the soil samples that I was involved in the research in Northern Australia. I mean, it's just bizarre that these critics keep raising these claims when in the literature we can document that there are these problems that they're trying to deny, and they're denying them to rescue the methods.
Okay. Okay. Let's talk about polonium halos. Um, uh, you talk about this a lot. In fact, this is actually specifically to your research in the rate participation in the rate study. Could
Yep.
you speak on that for a second?
Yes. Well, when uranium decays, it spits out the alpha particles, and so you can have, for example, a very tiny zircon crystal inside a larger biotite flake. And the alpha particles come shooting out. They can actually, because the zircon crystal is so small, the alpha particles actually leave the zircon crystal and shoot out into the biotite, surrounding biotite. But it's like a gun. You fire a gun at a drywall, you're going to leave a hole. And the alpha particles are energetic. They damage the crystal, the biotite crystal. But they can only go so far before they stop and run out of energy. And where they stop, they do the most damage, and they leave a ring, a darkened ring or halo. And because there are 8 alpha particle decays at 8 steps in the uranium decay chain with different energies, different bullets, you can actually see the central zircon crystal, and around it you see these rings, 8 different rings. And it was actually Robert Gentry who pioneered this work in the 80s. He actually showed how you can identify each of these rings according to the energy of the parent isotope that produced the alpha decay. And they match the alpha decayers in the uranium decay chain. Now, 3 of those, the last 3 steps are polonium 218, polonium 214, and polonium 210. And what was found and what we find is we find these halos that are only have rings from those polonium isotopes. In other words, the polonium must have been separated from the uranium when the uranium decayed down to polonium, separated and formed in one location to produce its own halos. So we find we've got polonium 218 halos, polonium 214 halos, and we've got polonium 210 halos. But here's a problem. Polonium 218 has a half-life of just over 3 minutes. Polonium 214 has a half-life of 160 microseconds. Polonium 218 has a half-life of 108 days. Very, very rapid decays. How could you possibly get these halos produced if the polonium's got to get separated before it decays away? It means it had to get separated very quickly. There had to be a lot of uranium decay almost saturating the system with polonium so it could be transported and nucleated somewhere else before the polonium could decay away. And so this creates a whole time issue problem. You know, we showed in the rate project that it requires 100 million years worth at the present decay rate of uranium to produce a good radio halo. But if it took 100 million years, the polonium would have all decayed away. It decays so rapidly. It wouldn't get separated from uranium unless the decay rate of uranium was so speeded up that it produced enough polonium quickly enough that could form halos before it all decayed away. I mean, so this became an argument for accelerated nuclear decay of uranium. And that meant that if uranium had decayed more rapidly, then the decay rate of the age of the rocks was much less. Furthermore, because excuse me, because these are typically found in granites, and geologists conventionally say it takes 100,000 million years or more for a granite to cool from a molten magma and crystallize, that if it took that long, you wouldn't get the polonium radiohalos in the biotite crystals in the granites. But they're there, loads of them. And I'm finding them in all sorts of places and documenting them. That's what my research is been about and is ongoing.
Right. And let me ask you a question. A friend of mine brought this up to me the other day. I looked over it and I was like, okay, we probably would, me and Dr. Snelling wouldn't have time to actually go over the points of that. But I told him I would ask you if you are aware of his particular arguments. Are you aware of a guy named Lawrence Collins? I think it is.
Yes.
Are you aware of his arguments? He has some kind of response to your, I think it was
Yes,
your
he's
claim.
emeritus professor. He's an emeritus professor at University of California, Northridge, and he talks about myrmekites, and these are being the polonium radiohalos are actually radium halos, which no one in the conventional literature has taken up his arguments and validated them. His whole idea about granites not forming from molten rock has is not accepted by the conventional community. These radiohalos are correctly identified as polonium. Radium halos would give you different ring sizes. And so I'm aware of his arguments, but no conventional scientist has his arguments haven't found traction within the general scientific community at all, even though they'd love his arguments to be right so as to disprove the creationist arguments.
All right. My next question is, what are fission tracks? Exactly. I know you talked
Well,
about these two.
yeah. Well, sometimes uranium 235 atoms will split. Instead of decay, they'll split. That's what happens in a nuclear chain reaction. You know, they target enriched uranium that's been enriched in uranium 235 with a neutron beam, like a trigger, and the atom splits and it produces a chain reaction which produces the bomb. But you get splitting of atoms, uranium 235 atoms, naturally. It's a very slow process. And so it breaks apart and it produces two daughter nuclides, daughter isotopes that are similar size, but they're very large and they break apart and go in different directions. They damage the crystal and the host crystal. And so if you etch the crystal with a little bit of acid, it actually reveals the tracks or damage trails. They're called fission tracks, and you can look at them up under a microscope and you can count how many fission tracks there are. You know the rate at which fission occurs, and so fission track dating is another dating method that's being used.
Um,
And so the point is, Brian, that both radio halos and fission tracks are evidence that physical nuclear decay has occurred. It's not simply a matter that, radioactive dating isn't a matter you do a chemical analysis and maybe it's just a chemical analysis and not actual radioactive decay. No, actual radioactive decay has occurred.
right. We're not going to delve too much into this, but since we are talking about radiometric decay, uh, radiometric decay also give off a lot of heat. And so some people argue if that much radiometric elements had decayed that fast, that rapidly, all at once, it would create a what they call a heat problem. What would be your response to that?
My response to that is very simple. We know that radio halos and fission tracks, if you raise the temperature, on a rock, they will obliterate. Why? The reason is that the crystalline lattice has been damaged by the alpha particles or the fission tracks, and when you heat the crystal, the atoms are going to vibrate and they're going to zip back into their original position, and the damage is going to be undone. And what temperature is that for radio halos? Well, I referred earlier to that geothermal drill hole at Fenton Hill near Los Alamos in New Mexico. Samples were taken all the way down in the granite, and they looked at the radio halos in the biotite crystals. And when the rock got to a temperature of 150 degrees Celsius, all the radio halos had been obliterated. So in other words, it only takes 150 degrees Celsius, and that's geologically cool. I know it's above the boiling point of water, which is hot for most people, but a granite forms at temperatures of 650 to 700 degrees Celsius. A lava from a volcano comes out at a temperature of over 1,000 degrees Celsius. That's hot. So if there was a heat problem, there'd be no radio halos, because a lot of heat would have annealed or wiped out all the radio halos. The very fact that we find radio halos in the rocks today still implies that the rocks have never been at a temperature above 150 degrees after they form.
That's
and so to me, that means there is no heat problem.
So
Where did the heat go? Russ Humphries has looked at ways in which the heat generated by accelerated nuclear decay could have been dissipated.
Right. That's a great answer. Essentially, what you're saying is that even if we don't know the mechanism by which the heat is alleviated, the fact of the matter is that doesn't take away the evidence that we know that accelerated nuclear decay has happened. So, in other words, if there was a heat problem,
and also doesn't take away the evidence. That's right. It doesn't take away the evidence that accelerated decay has occurred, and it doesn't take away the issue of the non-annealing of the radio halos. The radio halos indicate the rock has not been subjected to a lot of heat.
Right.
So that is actual physical evidence that there isn't a heat problem.
Right. All right. I want to ask you, I know you alluded to the fact that critics will try to attack you personally, and I've seen critics try that with you, Dr. Snelling, that they will try to sit there and attack you and try to discredit you or something like that. And I asked you this question through email earlier. Because another critic had brought it up to me, and then you answered me through email. But I just wanted to make sure, be able to set the record straight concerning some people have accused you online of being inconsistent, where some of your other stuff that you did, like I think you said you worked for a what was
mining
it?
company.
Yeah, and yeah, the
We're referring to an article, a paper I wrote for a volume on the geology of Australian ore deposits. I wrote a paper for the mining company on the geology of the Koongarra uranium deposits. And in that, I refer to the host rocks. And the critics will quote what I wrote. What they don't quote is the reference that I used for the source of that information. I quoted the conventional literature. I didn't say I believed them. I believed it. I just said, this is what the literature says about the age of these rocks. They neglect that point. The editor of that volume knew I was a creationist, and he said, right, well, you have to write the paper in such a way where you reference the source of the conventional claims about the age of these rocks. And that's exactly what I did. In your question you sent to me, you give the quote that the critic gives, where I said, where is it that I said, here it is, that I said the Archean basement consists of domes of granitoids and granitic gneisses, the Nanambu complex, the nearest outcrop, etc., and then I give the age as 870 to 800 million years, 800, but he leaves out the reference. I was quoting the literature. I wasn't saying that's what I believe. I was saying this is what the literature, this is a conventional date for these rock layers. Now, here's an interesting point to make. Creationists use the term Cambrian. Creationists use the term Precambrian. Why do we use those terms? Because those terms are labeled on rocks. We don't use them in terms of age. We just use them in terms of labels on a rock, because Cambrian rocks sit on top of Precambrian rocks. They're relatively younger than Precambrian rocks. And so we use the same labels, but we don't claim that there are the ages. You will go to the creationist literature and you will find referring to, the Cambrian to peat sandstone. Well, that's what they refer to in the literature. I'm using the term Cambrian in terms of a label, Cambrian as opposed to Permian, Coconino sandstone, which is higher up in the sequence of the Grand Canyon. It's a younger pancake in the stack of pancakes. And so we use those terms. Their terms originally, Paleozoic, Mesozoic, Cenozoic, were produced by flood geologists who believed in the flood. Old life, middle life, young life. Pre-flood animals buried in the flood, old life. Cenozoic, new life, life that existed after the flood from the animals that got off the ark. I mean, these were terms that were there before the millions of years. So the millions of years have been tacked on to that terminology. Just because we use the same terminology, doesn't mean we believe in the millions of years. We're just using the same labels so that we all know we're talking about the same rocks.
That's what I was going to
But
say.
it's wrong to accuse me of having a double standard,
Right.
because people knew I was a creationist. I was open about it, but to publish in the secular literature, I had to reference the conventional dates, and I gave the references. I didn't say Snelling says this is the age of the rock. I said this is Needham and et al., which was one of the authors of the paper I referenced on the geology of the Pine Creek geosyncline. I mean, it's ludicrous. They selectively quote and leave out the source, and to me that is very dangerous. We get accused of selective quoting. Our skeptical opponents are even worse at selective quoting.
Right. In other words, it's basic communication. We reference these things for communication purposes. Like, for example, I'm a scholar, so like there's a document called the Gospel of Thomas. Nobody thinks Thomas wrote that document. No one thinks that. It's like second century, second, third century, somewhere in there. But we still refer to it as the Gospel of Thomas because that's what it's called. And so we want to make sure everybody knows what we're talking about, the same thing, even though nobody thinks that it's first
Correct.
century or written by Thomas or anything like that.
Exactly.
So, okay. Thanks for clearing that up. I just wanted to set that to straight because some people do
Yeah,
bring that kind of stuff up. Like you said, people just attack you when they can't deal with your arguments, and that's
that's right. And
now.
it was first raised in the mid 1990s by Dr. Alex Ritchie, who was a paleontologist at the Australian Museum in Sydney, and sadly he passed away recently. Really nice guy. I liked him, but he just didn't agree with us, and so you attack the person rather than the arguments to try and make them look like they're a non-scientist, or they speak with double talk out of different sides of the mouth.
Here's one that I've heard a lot from people. People say, point to oil industries depend on radiometric dating being reliable to find oil deposits and drill for oil. What do they mean by that? And is this true, or because it's kind of hard for me to find out why they would be able to rely on the reliability of radiometric dating?
It's not true at all. It's not true at all. It's absolutely false. I always remember when I was doing my PhD studies, a professor came from the University of Witwatersrand in Johannesburg, and he said to me, "There's a parable, an African parable. If you want to find elephants, you go to elephant country." He said, "If you want to find gold deposits, you go to gold country." How do we explore for gold deposits? Well, we go to country rocks that we know from known ore deposits, known mines. What are the host rocks? Well, let's go and look for host rocks that are similar somewhere else, and let's test them for gold. Let's drill them for gold, and we find that's the case. I mean, a very classic example is an Australian geologist went to Michigan and looked at the copper deposits in Michigan. And he studied them and he found they were associated with basalts. He came back to Australia and he did gravity and magnetic surveys, which detected basalts 400 meters, 1,000 feet down. They put a drill hole down. The first drill hole went straight through copper ore in basalt because he went from the known and used the. So for example, you explore for uranium, okay? I used to get dropped by helicopter into stream beds. We collect stream sediment samples and analyze them for a whole suite of elements because we know if there's an ore body nearby, it's going to have a higher concentration of those elements in the soil. It's going to get washed into the stream, and so we'll detect. That's how we discovered diamond deposits. We look for the minerals that are shed from the host rock of a diamond deposit, and it's nothing to do with the age. The oil geologists will go to a sedimentary basin where there's layers of stacked pancake of sediment layers, and they'll look for samples of fossilized wood. And if the wood is carbonized, they'll take a polished surface, and reflect light off it. And if the light reflectance is a certain value, they know that the wood got to the point where the saps and waxes and resins and saps got boiled out to form the oil. And they call it the oil generation window. And so they know that oil has been generated in that sedimentary basin, so they'll know to go and explore in it. It has nothing to do with the age at all.
Why do they say that, do you think?
Sorry, why do they say that? Because they're trying to prove they want the millions of years, because the millions of years means that everything's evolved, which rules out a creator, which means there's a God that we're answerable to because we've sinned against him. It's a spiritual issue. It's not a scientific issue. You don't need to know the age of a rock to determine whether oil has been generated from that rock or it's yet to be generated. I mean, we know that the oil generation window, and if a sedimentary rock has passed through that window because of the reflectance of the organic material in it, then you know you can go and drill in there. And then you go and look for, the oil has migrated out of the source rock. So then you go and look for places where the oil might have pooled, traps, and then you drill into those, and that's where you find the oil. It's not rocket science, and it has nothing to do with it's nothing to do with the age of the rocks.
Literally not rocket science.
No, and it's the same. You'll do soil surveys to find. So, for example, some gold deposits are hosted by rock with magnetic minerals in it. So you do an airborne survey to find higher levels of magnetic rock. And then you'll go in that area and you look at the soils to analyze for gold. And if you find elevated gold content with a magnetic high, then you drill because there might be a gold deposit that's hosted by magnetic rock. I mean, that's nothing to do with the age of the rock at all.
Tim Clary, he actually worked for these oil companies going all over the world.
Correct.
Um,
Correct.
so you guys have actually worked with the oil business and that sort of thing, and radiometric dating has zero to do with whether.
No, no,
So,
no.
uh,
When I was working for leading mining companies in Australia. They're now international giants, and we were in there. I was in their exploration teams. I was doing research for them on exploration methods. We never did a radiometric date of a rock. We're always looking at the types of rocks. We're looking at the chemical analyses. We're looking at soils. We're looking at geophysical properties. We were doing airborne surveys. We were doing soil sediment sampling. We're doing stream sediment sampling. We're actually doing real science, collecting samples and sending them to the lab. Where we got elevated values and anomalies matched, we knew that we could drill them, and then we actually drilled to find out whether there was oil or coal or gold or copper, etc. there.
all right. You have a three-part series on answers in Genesis on radiometric dating, and on your part three, making sense of the patterns, you had said that the although the science or the although the radiometric dating has assumptions, the science behind radiometric dating is sound in terms of radiometric decay, decaying from one element to the next. And you said that it can have some useful properties for things like
Yes.
geology. Could you explain those?
Well, yes, I can explain it. It's easiest this way. You get a lava flow. Say we're looking at the flood as a flood geologist, and so the flood was a year long. It means a lava flow in the first month of the flood would have subsequently, because of accelerated nuclear decay, would have experienced 11 months of accelerated nuclear decay during the rest of the flood year. A lava flow that was spewed out at the end of the flood may have only suffered 1 month of accelerated nuclear decay, and so it will give you a younger radiometric age than the one that was deposited early in the flood. So you can figure out the relative difference between these, and we did that. I found that out with fission tracks in the rate project. I took volcanic ash beds from the bottom of the Grand Canyon, and sure enough, there was 500 million years worth of fission tracks in it. I took a lava ash beds from the Morrison Formation, which would have been middle of the flood, and sure enough, there was 160 plus million years worth of fission tracks there. And I took a lava flow, a volcanic ash bed on the present surface near Kingman, Arizona, and it had very few fission tracks in it because it was very recent. And so the relative order matches. And so, fission tracks, radioisotope dates or radioactive dates can give you relative ages in the sense of this one is older than that one, etc. You could also look at them as a geochemical property. So, for example, we know that this rock in the Grand Canyon gives this radiometric age. If we go to Australia, we might find a similar rock with a similar radiometric age, and lo and behold, it's in the same position in the sequence of rock layers. So maybe these two rock layers were formed at the same time relative to one another during the flood in different places at the same time. And so, it could be still be very useful. Yes, we have to recognize the assumptions, and one of those assumptions is that decay rates have been constant. We know they haven't been constant, but if they've been accelerated systematically, then they give systematic ages, then we can use those as relative ages relative to one another, and we can treat the we can treat the radioisotopes as geochemical properties of the rocks, just as we look at the fossil properties of a rock. We can compare a rock here in the Grand Canyon that has trilobites with a rock somewhere else in the world that has similar trilobites, and lo and behold, they fit at about the same level in the sequence of rock layers. Well, maybe that's because those types of trilobites were all fossilized at the same time during the flood, and so it goes on.
Right.
We can treat these as properties of the rock layers, and so they're still useful.
Okay, awesome. We're reaching the end of our discussion. I was wondering if you wanted to give your final thoughts and summary conclusions. Maybe give some thoughts on the way critics tried to attack y'all's position, and it's there's a from based on my conversation with you today, it does sound like it almost sounds like okay, the skeptics are arguing this, but they are completely ignorant of what's going on in the literature, what secular scientists are doing, what can be done. And so it's like it's coming from a lot of these criticism are coming from uninformed backgrounds that it's bringing to the table. Is that my understanding from you that there it's coming from this?
It's true. That's partly true. A lot of the bloggers are of that ilk, but some of the conventional scientists that are well qualified are also critics. So it's not true to say that all the critics are uninformed. Some of them are very well informed. But here's the issue: everyone has a world view. That is, a pair of glasses, a set of assumptions that they use to interpret the evidence around them. And so, why is it that we can all look at the same rocks in the Grand Canyon, but come to different views about how those rocks form? It's because we each have different views or assumptions about what happened in the past. We assume, based on an eyewitness testimony in the Bible, that God created, there was a beginning, and that there was a flood in which things happened catastrophically and accumulated all these dead things in rock layers, buried all around the globe. Whereas another scientist who doesn't believe the Bible is a valid historical document will say no. The Earth came out of the sun as a hot molten blob 4.5 billion years ago. Life evolved. Geological processes were slowly accumulating the rock layers, etc., etc. And millions of years are part of that process, and life evolved. There was no God who was involved, or if he was, he used that process. And so a different set of starting assumptions, the same rocks, but a different outcome interpretation. And I think we need to recognize that. We all have the same radio rocks. We also have the same radioisotopes. We can all do the same chemical analyses on the same equipment in the same labs. But it's how you interpret those analytical results will either give you an absolute age of millions of years or a relative age, because the clocks have ticked at faster rates in the past. And so it really is your assumptions. And like I said before, we need to be careful we don't throw the baby out with the bathwater. There is a geological column. There is a stack of rock layers that is real. There is an order in which those layers were formed. There are relative ages. The absolute ages are relative because of the assumptions that are derived to obtain those ages. The methods are good. They work to give results, but it's what assumptions you use that will give you those results. And so it's not the analytical equipment that's at fault. It's how you use the analytical results, which is based on the assumptions of the user of the results. And so that's why I would caution everyone to recognize that it's not just a matter of science, it's a matter of beliefs. What are the beliefs of the scientists who are making the statements to you? What are the beliefs of the scientists who are attacking the scientist who has different beliefs? I'm attacked because I'm a Christian who believes in a creator. I'm attacked because I believe that millions of years are false. And so I'm called a non-scientist because that's regarded as a non-scientific position. But can we scientifically explain how Jesus turned water into wine? Can we scientifically explain how Jesus took 5 loaves and 2 fish and fed thousands of people? No. The fish that he created was identical to the fish that the little boy's lunch, and he created it. And so, we have to recognize there are things beyond our understanding because God is eternal and all powerful, and we are finite and limited.
Right.
And so that's why we need an eyewitness who was there in the past who told us what happened.
Right. Um, and I know we didn't delve too much into this, but the Mount Vesuvius incident, it did have an eyewitness source. And so and because of that, that's how we were able to factor out the excess argon
Correct.
because we knew how over.
Correct. Exactly.
Now, I didn't bring this up,
Absolutely.
but some say that you could heat up the argon and get rid of the excess argon. But for that to happen, you'd have to know how much excess argon was in there to begin with. Is that right?
Correct. Absolutely. Again, you have to make assumptions.
Right. All right. Thank you for your time. We had a rocky start with all the technical difficulties, but we pulled through. Um,
Every pun intended. We had a rocky start to talk about rocks.
right, right, right,
Well,
right,
thank you very much because you've solved my problem in the process.
right. Well, my wife did. She's good at the tech stuff. She likes to call herself tech support. That's what her mom calls her. But
Yeah, that's right.
that's why I just kind of brought in a professional.
Correct. Correct.
All right, no problem. And thank you for your time. I appreciate
Okay,
it
you're
very
welcome.
much. I enjoyed it. I hope we do something else again. Maybe because that polonium halo thing sounds like it could be an entire video in itself with all the stuff that. Maybe we can delve deeper into that kind of subject matter later
Well,
on.
we'll see how you go.
Right. Thank you again, Dr. Snelling. I hope
All right,
everything
right.
goes good with you in Australia. And God bless. I appreciate your help.
Thank you very much. And just, you know where to find me.
Yep. Thank you again. God
Okay, bye
bless.
for now.
God bless.
Bye. Bye.
Thank you for watching Apologetics 101, and thank you for watching this video on Radiometric Dating with Andrew Snelling. I hope y'all enjoyed the answers. We dealt with some of the most common objections out there on the internet, so I hope y'all are really satisfied with those results. I'm sure I'm going to get a lot of people debating me on Radiometric Dating after this. I already got people debating me on the subject matter even before this video came out, so I imagine they will also once this video has been uploaded to YouTube. But in any given case, I'm expecting it. But I really liked talking about the subject matter with Andrew Snelling. I've always wanted him on my channel. He's the first geologist I've had on my channel too. So I'm hoping he's not the last because I'm hoping to try to get Baumgartner on here eventually. Um, but I wouldn't mind to discuss specific topics that we brought up in the discussion and kind of zero in on those with Dr. Snelling if he's ever willing to do another video, and that way we can kind of just focus specifically on that particular subject matter. But because this video deals with a lot of other stuff, we couldn't do that. So, but that's okay. The answers he gave were really good. I really enjoyed it. We had a lot of technical difficulties. Like I said in the introduction and during the interview, we had lots of technical difficulties at first. I've got stuff that happened on my end. He had stuff that happened on his end. My wife helped him figure out the problem with why he couldn't hear me. I could hear him, but he couldn't hear me. So there was nothing wrong with his microphone, but for some reason his speakers weren't working right. And so we had to fix that. That's what you heard us talking about that toward the end of the interview. But it was a great discussion, despite the devil's attempt to try to stop it. It went on, and it went on with a blast. It was awesome. and we got to deal with some of the most common criticisms out there online. So I was very satisfied with it. Um, and I hope you are too. Drop me a comment below and let me know what you think. And of course, don't forget, if you're not subscribed to my channel, please subscribe um, and hit that notification bell. Don't forget to give the video a thumbs up. I have lots of other videos planned up always. um, and I'm actually contacted a particular expert that I wanted to have on my channel, but he said that for me to contact him after mid-February. So some of the videos are going to probably wait until about next year. I do have my video planned up for Erica's egregious errors. I'm still planning on doing that. I have to find the video again and uh, and then publish it online. I think I've already got it. I don't think I might not have gotten it exported yet. I think I had to finish editing it, and I didn't finish editing it before all the legal stuff started happening with YouTube. I'll also keep you informed on that whenever my battle with YouTube goes ahead. I did a counter notification, and so I got showed the license, that legally allows me to be able to use this particular thing in either private or commercial use, as long as it follows Pixabay's terms of agreement and that sort of thing, and it does, and so. I'm waiting back for a response now, and then when that happens, I probably will produce a video discussing it. Maybe I'll drop a comment in the community page as well, keeping y'all informed of what happens there. All right. Thank you again for watching Apologetics 101. Thank you again for watching this video on radiometric dating. I've always wanted to do a video on radiometric dating, even before I did my Genesis series, because I did something else on Genesis that didn't pan out as well as the Genesis series did. But I wanted to do a radiometric dating video then. I wanted to do a full-blown video on radiometric dating. That's a subject matter that I'm interested in, not because I trust it or agree with it or anything like that. It's because I know a lot about it. And despite some of the critics on my channel trying to accuse, like Amazing Blue, trying to accuse me of not knowing that much, I know quite a bit about radiometric dating. I'm not an expert per se, but I do know a lot about it. But I would consider Dr. Snelling an expert on it. He was part of the rate team. He's written quite a bit about it. He's a geologist, so I do consider him the expert, at least in terms of young Earth creationists, as well as Baumgartner. I'm hoping to have Baumgartner on here eventually for a number of videos that I would like to produce. I know how to contact him. I can get his contact information online. My understanding, and I think maybe Snelling had mentioned it too in the interview, maybe. I think he did. That Baumgartner now works for Liberty University, which is my alma mater. So, that's pretty cool that he works for Liberty University. But his contact information is online, so I might be able to contact him and see if he'd be willing to do an interview eventually. I wouldn't mind doing one with him specifically on the contamination argument some people make on the C14 in diamonds, and just kind of zero in on that discussion. So I wouldn't mind having him on here for that. If I do, that will also be part of the Genesis series. So that's pretty cool. And I will see y'all on the next one. And until next time, stay in the know.